Now that we've talked about the laboratory technique of calorimetry to determine the change in enthalpy that occurs during a reaction, we're going to talk about another way of determining the change in enthalpy in a reaction, and that's by using Hess's law. Now, Hess's law states that if a reaction is carried out in a series of steps, then the change in enthalpy for the overall reaction equals the sum of the enthalpy changes for the individual steps. So basically, if you can add all the different steps up into one single reaction, then you can also sum up all of the enthalpy changes into one final enthalpy change for the entire reaction. Now, the reason why we can do this is because enthalpy is a state function. Remember that it does not matter the steps that are taken, only where you started and where you end up with. And this explains why, if a particular reaction can be carried out in one step or in a series of steps, the fact that the sum of the enthalpy changes is going to be the same, whether or not it's in one step or in thousands of steps. So as you can see here, this diagram represents Hess's law. So you have the overall reaction of methane reacting with oxygen to produce carbon dioxide and water, and if it's just completed in one step, then it releases 890 kilojoules. However, if it's completed in two steps, the first step releases 607 kilojoules, and then the second step releases 283 kilojoules. If you notice though, if you sum up those two reaction enthalpies, they equal 890 kilojoules. So it doesn't matter how many steps are required, you can just sum up the enthalpies and that will equal the enthalpy of reaction. Here are a couple of reminders before we get into the calculations for Hess's law. The first one is when you flip a reaction, remember that you need to multiply the enthalpy change by -1. Also, when you multiply the equation by a coefficient, so if you multiply the entire equation by 2, then you need to multiply the enthalpy change by that value, so by 2. So let's actually look at an example to understand how Hess's law helps us in order to calculate the enthalpy change for a reaction. So in this example problem, it tells me that I have carbon reacting with oxygen to produce carbon monoxide, and it's wanting to know the change in enthalpy that occurs in this reaction. Well, I don't know what the change in enthalpy is, but what I am told is these two separate reactions, which together can create this one reaction. Now, I have to manipulate these two reactions and these two enthalpies in order to determine the change in enthalpy for this reaction. So if you notice here, I've got carbon on my reactant side, which I want on my reactant side for my final reaction. So I'm going to leave that there. What you should also notice is that I have carbon monoxide on my product side, but I have carbon monoxide on my reactant side right now. And so what I'm going to do is I'm going to flip this reaction. And so instead of having CO on the reactant side, it's going to be on the product side. So CO2 is going to become the reactant, and that's going to produce carbon monoxide and 1/2 mole of oxygen. And so the way that I make up for the fact that I flipped this reaction is that my change in enthalpy is now going to be the negative of what it was before. So now it's going to be 283.0 kilojoules. All right? And now I think I can just simply add these two reactions together. I'm going to get rid of this one because I flipped it already. And what I should get is this reaction right here. So let's see if I can actually do that. So I have carbon. I'm going to simply add them together. I have carbon and, well, if you notice, on my right-hand side I have carbon dioxide, and on my left-hand side I have carbon dioxide. So these cancel because they're on opposite sides. I have 1 mole of oxygen here. I have 1/2 mole here. So if I were to move this 1/2 mole over to my reactant side, by subtracting, I would end up with 1 minus 1/2. That would just be 1/2 mole of oxygen. And that's going to produce what's left over, which is just carbon monoxide. So I have my reaction right here. Let's now, all we have to do is add the changes in enthalpy, and that will give me my change in enthalpy for the reaction I'm interested in. So when I add these two together, what I get is negative 110.5 kilojoules. And that's all I had to do. So it's just a matter of rejiggering in order to get the reaction that I'm actually interested in. For this next reaction, I have 3 individual reactions that together will give me this final reaction of 2 moles of carbon reacting with hydrogen gas to produce C2H2. So let's look here. Here, which is also acetylene or ethene, is on my reactant side, but I actually want it on my product side. And so what I'm going to do is I'm going to flip this reaction. So this becomes, I'm going to write it over here, 2 carbon dioxides plus water, and it produces my ethene and 5½ moles of oxygen. Okay. Keep in mind, since I flipped this, that my change in enthalpy is now going to be positive, 1,299.6. All right, I want my carbon to be on the reactant side. It is currently on the reactant side. However, there's only 1 carbon, and there are no other carbons here that I can add together to get it to be 2. So I'm going to have to take this entire reaction and multiply by 2, which means I'm going to have to multiply this by 2 as well. So I would write the reaction as 2 carbons plus 2 moles of oxygen produce 2 moles of carbon dioxide, and my new change in enthalpy is going to be negative 787.0 kilojoules. All right, now if we look at H2 here, I want H2 on the left-hand side. I don't want water. However, if you notice on this side, I have water, so I'll figure that out. So right now I'm going to leave this one alone. So I'm going to write it again over here just so I can add up my reactions. Remember, the number of steps that you take to get the reaction doesn't matter, and it doesn't affect your enthalpy. All that matters is what you start with and what you end with. So I'm going to look at this now, make sure that this works out. I have 2 carbon dioxides here, which I actually don't want at all in my reaction. But if you notice, I have 2 carbon dioxides here, so they cancel. I have 1 water here, which I don't want in my final reaction, but notice I have another water right there, so they cancel. Let's see if anything else cancels out. I've got a crazy amount of oxygens. Here, I'm going to convert this really quickly into a fraction to make my life easier. It would be 4/2 to be 2. So I have 4/2 plus 1/2 because they're on the same side. That's 5/2 total. But notice I have 5/2 here. So since they're on opposite sides, they also cancel. So all I'm left with is 2 carbons, 2 moles of carbon, plus hydrogen. And that produces my C2H2. So all I have to do now is take my changes in enthalpy and add them up, and that will give me the change in enthalpy for the reaction that I was concerned with. And what I get is 226.8 kilojoules.